All right, hello everybody. So I thought it might be helpful for me to do a screencast of section 20.4, which is on standard cell potentials and electrochemistry, because it's not super intuitive and it's kind of hard just to grasp by reading the textbook. I tried to kind of flesh it out in my slides, but I figured the best thing would be for me to kind of talk over what I was thinking about, just to make sure that you're grasping the material. So before you do anything else, I need you to read the textbook chapter, section 20.4, because the textbook does a great job of all of these example problems, and I think you get more from it from seeing all of the example problems in the textbook, which I wasn't just going to like copy and paste into the slides. Then, when you've done that, go ahead and read through my slides, and if you're still feeling confused, that's when I would suggest using my screencast. These are really like bare bones slides, and so that's why you do really need to do the textbook reading before you go ahead and complete the practice problems, which are due on Friday. All right, so 20.4, cell potentials under standard conditions. So this section centers around the question, what leads to the spontaneous flow of electrons? And the short answer would be that electrons flow from the anode, so this guy over here, to the cathode due to a difference in potential energy. Before I go any further, what is this potential energy that I'm talking about? So the potential energy we are talking about when it comes to voltaic cells is the potential for the anode to become oxidized and the cathode to become reduced. So, as you can see in both of these pictures, the electrons are flowing away from the anode and towards the cathode. And the reason for that is the cathode is always going to have a more positive potential energy than the anode, and electrons, being negatively charged, are going to be attracted towards the more positively charged electrode, which again is always going to be the cathode. And so when the electrons flow from the anode away from it, it's losing electrons, it's being oxidized, and the cathode over time is gaining all of these electrons, so it is being reduced. And then the difference in potential energy between the cathode and the anode is measured in units called volts. So now let's talk about cell potential, or E cell. So cell potential is the difference between the two electrodes, so the cathode and the anode in a voltaic cell. The cell potential is always positive because the magnitude of the cathode should be greater than that of the anode, and the cathode is always more positive, so you should always have a positive cell potential. But the exact magnitude depends on a couple of different factors. The specific reactions that are occurring at the cathode and the anode, as always, temperature. We're going to assume that we're working with 25 degrees Celsius or room temperature unless otherwise noted, and then the concentrations of the reactants and products. For us, we're just going to be assuming that everything is at standard conditions, so we're working with that 25 degrees Celsius room temperature, 1 molar reactant and product concentrations, and a single atmosphere of pressure when we're doing these problems. So when we're doing these problems at standard conditions, we now call the cell potential the standard cell potential, and E cell becomes E naught cell, and this naught just means that we're at standard conditions. So the standard cell potential is the difference between the half cell potentials at the cathode and the half cell potential at the anode. By convention, the potential associated with both the cathode and the electron is chosen to be the potential for reduction. It could have been oxidation, but scientists chose to focus on reduction. And this is why standard half cell potentials are denoted often as E naught red for E naught reduced. So that's why you'll see it that way. And then it does come along with a formula. This is really, for right now, the only formula you need to know. The standard cell potential is the standard reduction potential of the cathode minus the standard reduction potential of the anode. So to me, this by itself doesn't make a whole lot of sense. I want to clarify it further when we do a practice problem. But quickly, before we do a practice problem, you will notice on slide 25, I included table 20.1, which is a bunch of standard reduction potentials for different chemical reactions in water at 25 degrees Celsius. And the question is, well, how exactly are you getting these reduction half potentials? And the answer is that it's actually not possible to measure the standard reduction potential of a half reaction directly. Instead, we call the reduction of hydrogen 0. So everything else is just relative to the standard reduction potential of hydrogen. And that's why you see hydrogen over here and everything's either above or below it. It's more positive above and then more negative going below. All right, so I think this will all kind of sum together in this sample problem. And by the way, you can find it on page 872. I took it right out of your textbook. So question reads, use table 20.1 to calculate E0 cell for a voltaic cell in which the following chemical reaction is occurring. Your first step, so this is the complete reaction. I did do a mental check of the charges on both sides as well as the number of atoms on both sides. Everything balances. So we're going to go ahead, you should also always check that. We're going to go ahead and split this into two different reactions. So I split it into two different half reactions down here, chromate and water. So this is the chromate ion, so chromium and water to make the chromate ion and water. And then 6 minus iodine to 3 iodine. So I just matched up all my atoms on both sides when I was tearing apart these two half reactions. So that was step 1. For step 2, and sorry that this gets kind of small. Let's see. A little better. My dinos are in the way. I really wanted to include the dinos. There we go. So when we pull the reaction apart, you'll notice that the charges on each of the half reactions become imbalanced, and we need to fix that. And so we add electrons to both sides to fix the two half reactions. When you recombine the equation, those electrons cancel back out and you get to the original equation, but we need to put them in to balance the charges on both sides in our half reactions. Step 3 is to determine which of the half reactions is being oxidized and which one is being reduced. Remember that reduction happens at the cathode and oxidation at the anode. So in this case, this reaction is gaining electrons, so it's being reduced, and this reaction is giving away electrons, so it's being oxidized. Reduction, cathode, oxidation, anode. All right. So now we're going to use table 20.1 on slide 25 to determine the standard cell potentials for each of the half reactions. So first off, we've got this guy. And we can look them up. So Cr2O7, this looks about right, plus 1.33. I keep going to the wrong side, don't I? Oh, I'm just losing it. There we go, positive 1.33 volts. And then iodine, I also reduced this here. And when I reduce it, and oh, one other thing I forgot, now I'm really using it. So this, remember, is an oxidation. The problem is you're not going to find it written out like this on the standard table of reductions. So what you need to do, and it's really easy to go from oxidation to reduction, I just flip the equation. So now when you flip it and you reduce it, you'll find it here as 0.54. So that's the other important step, is you need to flip the equation that's being oxidized. Then, last but not least, you take the E0 red at the cathode minus E0 red at the anode, so 1.33 volts minus 0.54 volts, and you get 0.79 volts, and that is your standard cell potential, and that is how you find the standard cell potential. Last but not least, strengths of oxidizing and reducing agents. The more positive the value of your E0 reduction, the greater the tendency for reduction to happen under standard conditions. So the reduction at the cathode should always be more positive than that of the anode. That's why the electrons are flowing towards the cathode in the first place. Table 20.1 lists half reactions in order of decreasing tendency to undergo a reduction. So my reactions that like to undergo reduction are at the top. Halogens make great oxidizing agents because they're easily reduced because they really want electrons. And then at the bottom, the half reaction with most negative reduction potential is the one that's the most easily reversed and run as an oxidation. All right, so go ahead, do the practice problems, and let me know if you have any questions. Good luck.